one of the main things that comes out of it is we can come up with a rate expression, and we can get the orders of the different reactants or things within it. Okay? And that's our standard kind of kinetic argument that we would learn from 152. And to determine all those orders, we have to go and do experiments with all of these. But when we go through and actually look at an experiment, more than likely what's happening is we're plotting a rate versus a concentration, and we're trying to see that relationship and what things can kind of come out of it. So if we looked at just a standard, straightforward substrate to product reaction, and assuming we have a linear relationship, so just a one-for-one, we would see a pretty much straight line. Yes, I goofed the plot. Don't give me too much of a hard time on that. So that point should be a little bit higher. But it's effectively a straight line. So we're saying first order rate. So it's just based solely on the substrate concentration. When we now move to enzyme kinetics, okay, or our standard enzyme substrate relationship, we're going to see a slightly different plot come out of that. Okay? And that plot is ultimately dependent on what's happening with the enzyme concentration. Okay? So let's just pick an enzyme concentration. Doesn't really matter what it is, but let's just pick some value. Okay? Its whole goal as an enzyme is to speed up the rate of the reaction. So at low substrate concentrations, okay, we would expect a low rate because the odds of the substrate encountering the enzyme are still relatively low. So if we were going to then kind of draw on top of this and do some kind of prediction, hopefully the blue will show up. We're still going to be starting somewhere near the bottom, just like we did with our standard reaction. Okay? But then what happens as we add more substrate? What should happen to the rate? It should increase. Should it increase faster or slower than the standard process? It should go faster, because that's the whole point of the enzyme, is to speed the reaction faster. So we'll probably see it go up relatively sharp, okay? At least in comparison, let's actually make it a little more dramatic, at least in comparison to our whatever that other one is, the standard reaction. Okay.
So is it more of a hyperbolic?
That's what we'll get into in just a second here. So as we add more and more substrate, we would expect the rate to increase up to a point. What's that point?
The saturation.
It's the saturation of the enzyme. We've now put in so much substrate that the substrate is now floating around waiting to be turned into product. Okay, well, if it's waiting to be turned into product, what happens to the rate?
It slows down.
It's going to start to slow down. Okay? And we have to be a little bit careful there. What we're saying is slowing down is not the rate of the reaction, but the change in rate of the reaction.
Right.
Okay? Which means that our line does not turn and go down, but it kind of flatlines. It kind of plateaus.
Because your rate never decreases.
Your rate will not decrease. So what's happening at that kind of peak off, or where that flat line comes in, is that we've now oversaturated the enzyme. The amount of substrate is so excessive in terms of the enzyme that the enzyme can't process the substrate fast enough into product. So we see this leveling off. Okay. Well, with 152, when we're looking at just standard substrate to product relationships, that's a straightforward solve. It's a linear relationship. When we move into biochemistry, do we have a straightforward linear relationship? No. Okay, and that's where this becomes tricky. Okay. Take it a step further. What happens if we move into something along lines of cooperative binding? Okay. Still an enzyme plus our substrate generate our product, but what happened in cooperative binding? We get a sigmoidal, because what ends up happening is as the enzyme binds, okay, yeah, we might have, and it's always blurry at the bottom, we might have some binding, but then what's going to happen is that as we bind some, even more binds. Okay? It binds faster. So instead of our rate just being kind of a nice even slope, we end up getting this kind of S-like shape. Okay? And theoretically, it would cap out at the same level if we assume everything's consistent. Okay? So again, we'll see that plateauing because we've now added so much substrate that the enzyme can't turn it over. So these are some of the kind of basic shapes that you can pick up out of these curves. Okay? A standard reaction with no catalyst or enzyme, we in theory just get a straight line. There are variations of that, but that's our simplest application. With an enzyme, we expect this hyperbolic curve that's shown in blue. With cooperative binding, we expect this sigmoidal shape. Okay. So let's take a look at that hyperbolic curve, because thankfully we aren't going to look at the kinetics of the sigmoidal shape. Can we make some approximations or simplifications off of our hyperbolic curve? And I know that's a vague question. What can you tell me about low concentrations?
At the rate at which the substrate is being converted to a product, as much happens, that's concentration and that's time. It happens more relatively quickly.
So it is going to happen faster than our standard reaction, but that's something we would kind of predict. Okay? But let's say low concentrations. So let's erase that line so we don't see that anymore. By low concentrations of our substrate, or in this case A, I'm saying at 2. Anything underneath 2.
The rate is going to be low.
It's not even really that, but you're right, it is relatively low. So and it's not exactly the same, and that might be where you're getting at. So what I'm asking you to do is now, when you look at this curve, you see everything from roughly 0 up to 10. What I'm asking you to do is not look beyond 2. At low concentrations, between 2 and 0. So what I'm asking you to do is now pretty much erase all of that. It's linear. So at low concentrations, I have a linear relationship. Right? What happens if I look at high concentrations? Whoops. So now let's say everything from 4 on. And we ignore everything else. Also starts to pick up this linear relationship. Okay? So when we're looking at the enzyme kinetics, we really have 2 parts of our curve that are linear. And yes, there's this weird gray area where we transition between those 2 linear relationships. Okay? But we do have those 2 linear relationships, and that can help us simplify our analysis, theoretically. Okay? So that's kind of one of the big conclusions that they're trying to get at when we're looking at the enzyme kinetics, is we can break it down into 2 separate conditions. Okay? And so when we go through and try and evaluate the kinetics of our reaction, what we want to do with our expression is make sure that it satisfies both of these conditions. At high substrate concentrations, I get a linear relationship. In a linear relationship with virtually no change in rate. And at low substrate concentrations, whatever my equation may be, what I want to be able to see is a linear relationship, again, with a very fast change in rate. Okay? So those 2 conditions need to end up getting met when we go through and look at the kinetics of the overall reaction. Okay? Questions on that?
So how many types of curves are there? There's 3.
So
linear, and then the
when we're looking at these enzyme connect, this rate versus concentration of substrate, we really have 3 types of curves. We've got our what I'm just calling linear, but this is, remember, this goes back to the order of the reaction. Okay? In the order of the reaction, our linear only happens if we're first order. If we're second order, we get a parabolic curve. Okay? If we're third order, I think that goes hyperbolic. I'm not sure. Okay. So without an enzyme, you do have a bunch of variations for possible curves in the substrate to product. Okay? The one that we tend to focus on primarily is just our first order, okay? Which gives us the linear relationship. Okay? So I want you to be aware that there are other possibilities, but those other possibilities are rarely talked about at this level, mainly because we don't really care about them. So we're looking at a linear relationship with just our substrate to product, okay, with the potential for others. Okay, potential for, I think it's parabolic. Pretty sure it's parabolic for the second order. Oh, right, freaking pen. Second order. And then I think it's hyperbolic. Anybody know for third order? I think it's hyperbolic for third order. And I'm not sure it's actually discussed in your textbook. What you would do is plot it and look at it. And I think it's hyperbolic. So all 3 of those are potentials for just a standard substrate to product reaction, standard chemistry reaction. Okay. The one that we're primarily concerned about is just that linear relationship. When we move to our standard enzyme kinetics, now what ends up happening is we get this hyperbolic relationship. Okay. And that was this curve that looks kind of ugly, but it's close enough. Okay. And then our last condition is our cooperative binding, and that's your sigmoidal. Sigmoidal. Close enough. Okay, where you get that kind of S shape. Okay. So those are the primary types of curves that you can pick up. And so just looking at that plot, you could then pick up some of that information and decide what's happening within it. Okay. And yeah, if you take a look at the cooperative binding, you're going to have 3 regions of linearity at low concentrations, intermediate concentrations, and high concentrations. So thankfully, we don't look at that. Okay. So now it comes back to the kinetics and how we can start to actually predict the rates and what's happening with these. Because we want to come up with something to determine our rate constant. How fast is our reaction going to go? We want to be able to predict. Okay? So this would go back to your 152 basics. And we look at an individual reaction and we try and set things equal to each other to determine what the rate is so that we can figure out our rate constant and all this other fun jazz. Okay, so we have to come up with some way to design an experiment. So what you may or may not remember from 152 is that if we have multiple steps in a reaction, our rate is going to be dependent on the slowest step. Well, if we don't know what the slowest step is, we kind of have to evaluate everything together. Okay? So if we look at each of the individual steps, our enzyme reacts with the substrate to form the enzyme substrate complex. Okay? And we're just saying this is one direction. What does the enzyme substrate complex then potentially do? Well, it can go back to the starting material, or it can go forwards to reforming the enzyme and our product. So we've got these 3 individual steps that kind of stack through this. Okay? And if you, again, potentially remember from 152, this is a big complex process to go through and solve. Okay? So we have to make some assumptions. One of those assumptions that we're going to make is that we're going to assume we make it to equilibrium. Okay? And that equilibrium is going to center around the enzyme substrate concentration. All right? Which is actually on the next slide. So what we've got summarized here at the bottom is what we just talked about. I thought it was a little bit easier to see from the graph. At low concentrations, what happens? Well, now it's dependent solely on the enzyme substrate complex, really just K2. Okay? It's just dependent here. Because if I have a low substrate concentration, that's what's going to determine that reaction. Okay? At high substrate concentrations, I'm now concerned about the total enzyme concentration, because that's what's contributing to my ES species. Okay? What makes this challenging? If we look at low substrate concentration, let's not do that one yet. Let's look at high substrate concentrations. Okay. Do we know the total enzyme concentration? Okay, let's think about this. Why should you?
It levels.
Not even that. Okay, to do these tests, what are we doing? We're taking some substrate, we're taking some enzyme, we put them together, and we watch the rate of the reaction. So you took some enzyme. Do you know the concentration of enzyme that you put into the reaction? You better know. That's the whole point. So that's not too bad. We can determine that because we put it in there. The total enzyme concentration makes sense. Okay? But where are we going to run into an issue? What happened at low substrate concentrations? We're now dependent on the concentration of the enzyme substrate complex. When you start this experiment, you probably know the concentration of the enzyme. You probably know the concentration of the substrate. You can probably even figure out the concentration of the product. But do you know what's happening with the enzyme substrate complex? No. Okay. That becomes very challenging because I can't now solve at my low rate because I don't know the enzyme substrate concentration. And again, for those of you that were in 152, if you remember the situation, what you ended up having to go through and do is set it up as an equilibrium expression and rearrange everything and solve for some unknown concentration. And then use that to plug into your main equations to then go through and solve. And it's this big, long, drawn-out process. Right? And that's what we end up doing with biochem. Okay? So we assume that we achieve a steady state. Okay? So everything kind of balances out. So the rate of the formation of your enzyme substrate complex will need to equal the rate of its decomposition. Okay? So do we know the rate of the formation of the enzyme substrate complex? Okay. And again, we're going to have to make some assumptions. What's going to determine what reaction forms the enzyme substrate complex? The enzyme and the substrate and our rate constant for the formation. Okay. Do we know the rate of decomposition of the enzyme substrate complex? So if we're looking at the decomposition, we're of course starting with our enzyme substrate complex. Okay. What things contribute to its decomposition?
Don't you want to just look at your product side because the enzyme binds to the substrate and once it
So number one, we do see a decomposition of K2. Okay. Enzyme substrate absolutely decomposes to form product. But is that the only thing the enzyme substrate complex does?
No,
No.
you have the enzyme.
We also have the enzyme substrate decomposing into the enzyme plus the substrate. So when we're looking at the rate of decomposition of the enzyme substrate complex, it's not just our rate for K2, it's also going to involve the reverse reaction. So it's the sum of both of those rates that's actually going to determine your equilibrium. So what we end up with is this fancy little equation. Okay? K1 times the concentration of your enzyme times the substrate will equal K2 times concentration of the substrate complex plus K minus 1 times concentration of the enzyme substrate complex. Okay? So now what can we do with this? Well, what was our problem on the previous slide? Problem was we don't know the concentration of the enzyme substrate complex. So what are we going to do with this equation? We're going to rearrange it to solve for the enzyme substrate concentration. Okay? And we could do a variety of things. So this is one option. Grouping constants. Bear with me here for a moment. What happens with our enzyme concentration in the course of the reaction?
It goes down because it becomes enzyme substrate complex.
Exactly right. So do we know the concentration of the enzyme at any point during the reaction?
Just what you have in the beginning.
We just know what we started with. We don't know what the current enzyme concentration is. So it's actually a little bit more complex than we initially postulated. The enzyme substrate we absolutely do not know. The enzyme concentration here, through the course of the reaction, changes. What is that going to do to the rate?
Gradually slow.
Also going to change it. Okay? So we can't just solve for the enzyme substrate concentration. Okay? So what we ended up doing here was we grouped similar terms, and then we're going to hope to God that we can find some way to simplify this. So what we did was grouped our concentrations on one side, and we grouped our rate constants on the other, okay, just through algebra. Okay, everybody see what I did there? Are you okay with that algebraic step? Because the textbook's not going to show it to you at all. Okay, so I want to make sure you see what happened. All I'm doing is dividing both sides by the enzyme substrate concentration. The next thing that we can go through and do, and I should have actually stepwise this part, is if we look at our enzyme total concentration, what's it going to be equal to? Okay, so ignore the thing above it for the moment. If I asked you just for the enzyme total concentration, what should it be equal to at any point during the reaction? What's that?
Would that be what we started with, the concentration we started with?
So push it a little bit further. What happens to our total enzyme during the reaction? Does it always stay the enzyme? No. So what gives us the total enzyme concentration? The enzyme concentration with no substrate. Okay, just the stuff that's free flowing around waiting to find substrate. So we get that enzyme concentration.
Plus the enzyme substrate complex.
Plus the concentration of enzyme that is occupied in the substrate, okay, in our enzyme substrate complex. So we get this relationship. Okay. We don't know the concentration of the enzyme at any given instant. We don't know the concentration of the enzyme substrate. But we do know our total enzyme. So what we can go through and do is now take that information, and that's, whoops, come back here. That's what this expression is telling us. Okay. What we decided to solve for was just the concentration of enzyme, free enzyme, at any given instant in the course of the reaction. Once I know that, I'm then going to plug it into the equation. Okay. Why did I decide to plug that in? Because I probably tried to do the enzyme substrate concentration, solve for it first, and found out that that didn't simplify my equation. Okay, so then we tried the other one and found out, oh, that did simplify it. Okay, so what you're seeing here is not the how did we do this, but this is how it works. Right? So once we've got that enzyme concentration, we can then substitute that in. Okay, and we get this big nasty mess. So what we're doing is subbing in our total enzyme minus our enzyme substrate complex into the expression. Everybody see that sub? Okay, so this is then getting no, that's the wrong button. Come back here. This is getting substituted into here. And that gives us this expression. Okay. You'll notice that we did some other things there. Okay. K2 is what? A rate what?
A rate constant forms enzyme sulfur concentration to product.
Forming our products. But it's a rate constant. What is K minus 1? A rate
Constant for
constant. What's a constant plus a constant? A constant. What was K1? Also a constant. So what's a constant plus a constant divided by a constant? A constant value. I don't need to know what it is necessarily, okay, but it is a constant. So instead of it maintaining this expression with all these pluses and minuses and 2's and 1's and minus 1's, what did we end up doing is we said all of that equals a new constant. And that new constant I'm defining as Km. Okay? So we're bringing in a new term here because we're attempting to just simplify. Okay, yeah, and I know it doesn't look like you're simplifying, but that is what we're attempting to do here. Okay, so we now have this expression where we've got the total enzyme concentration, our substrate, and then our enzyme substrate complex all equal to Km. Okay? Well, we still don't know our enzyme substrate concentration. Okay, but what we can go through and do is rearrange this expression to now solve for it. Okay, so again, more algebra. Okay, should I go through the algebra? Is that a yes or a no? Okay, because really all it is going to be algebra. All we're going to do is then multiply both sides by our enzyme substrate concentration to get this guy over here. Then we'll collect terms, our enzyme substrates, and we'll end up with, see if I did this right, substrate, I'm trying to do it in my head. We've got ES times Km plus ES times, what was that, S? Okay.
Is that 25?
Where's it 25? Oh, I see what you're saying. Yeah. E. Okay. We can factor out the ES. And that stupid 14 is going to get in the way, so I'll just color over it. ES times Km plus our substrate. Divide both sides by Km plus our substrate, and what do we have? Okay, we've got that algebraic system. I know that's crammed in there. Kind of got it? Okay. All we're trying to do is solve for ES, that enzyme substrate concentration. The thing that's nice about this is, do we know the total enzyme concentration? Do we know the substrate concentration? Km is a constant, which theoretically, hopefully, we'd be able to solve from an experiment. Okay. So we now have a way to solve for our concentration of ES. What can we then do with this? Well, remember, what happens if our rate was slow? Or sorry, if our concentration of S was low. Okay. Well, what that said was that rate was equal to K2 times ES. Well, what was ES? ES is our enzyme total times our substrate over Km plus our substrate concentration. Okay. And if our rate is high, it's just K2 times E2. So on top of all of these symbols, for some reason, biochemists decided that the term rate was too confusing of a word, or too big of a word to write out. So what did they switch the symbol for rate to? V. Kind of makes sense, because it's the velocity of the reaction. Okay. And at high concentrations of S, what happens to our rate? Well, if we looked at our curve, what happened at high concentrations? It flattens out, and we achieve a maximum rate, and we can call that Vmax. Okay. So all these fun diddly squat things end up being rearranged, and we can end up with the expression for the Michaelis-Menten equation. Okay? And to do that, what we ended up solving for in that first case was K2. K2 is equal to V over ES. Whoops, that's an ES. K2 at high concentrations is equal to Vmax over your enzyme total. I keep putting that T inside the brackets. That's unintentional. What was K2? Say that again. What was K2? A rate what? Constant. So if our rate, if our concentration of S is low versus our concentration of S high, does the rate constant change? No, because it's a constant. So what do we end up doing? We can set these equal to each other. Vmax over our enzyme total concentration. From all that other stuff, we plug that into ES. Right, all this plugging and chugging and plugging and chugging and simplifications. And we end up with this overall expression, that our rate for an enzyme-catalyzed reaction will be equal to the maximum velocity possible for that reaction times the substrate concentration divided by Km. We'll talk about what Km is, but it's a constant, plus the substrate concentration. Okay. This means that if I know the substrate, if I know these terms, I can then solve for the rate at any given concentration. That's kind of neat. Okay. Odds that I know all of those terms is a different situation. Okay. But ultimately, all of this is driving for is to get here, which seems a little bit weird because this is not an easy expression to look at. Okay. But the whole reason behind all of this is actually not really to get here, but it's to change our graph. Okay. We want to make this graph as easy to interpret as possible. What type of curve is as easy to interpret as possible? A linear expression. So what Michaelis and Menton were going through and doing is trying to change their interpretation of the data so that they could then get it into a linear expression. So if we take a look at this Michaelis-Menten expression, or this equation, do you see a linear relationship? I'm going to guess no. It's okay. I don't see a linear relationship there either. So what did they do with it? They kept massaging those equations and numbers around. Okay. Oh, and I just jumped straight to it there. Well, that was mean. Let me jump. Wait, what? Oh, I shuffled all sorts of this stuff around. So we're going to jump back and forth. So if we take a look at our Michaelis-Menten equation, we get this observed rate. Okay? Just like you did in 152, our whole goal was to get a linear relationship. So what we want this equation to match is what format? What is the equation for a straight line? Substrate, or what's the equation for a straight line? Ignore biochemistry.
Y equals mx plus B.
Y equals mx plus b. That's what we're trying to match. How can we rearrange this to get us into that format? Well, we got a hint here. We take the reciprocal of both sides. Okay. If you do the reciprocal of both sides, you can then rearrange your equation into this format. What is y? Y is equal to 1 over the rate for your reaction. What is the slope of our equation? It's our rate constant, or our new constant, compilation of rate constants, divided by our maximum velocity. What is x? Our substrate concentration. What is b? 1 over V max. Why is this helpful? Because what do I do when I run an experiment? I take my substrate and I mix it with an enzyme and I can monitor my rate. So what things do I know? Substrate concentration and rate. If I know my rate, can I determine my 1 over my rate? Yeah. To obtain that rate, I had a given substrate concentration. Do I know, if I know my substrate concentration, do I know what 1 over my substrate concentration is? So what I can do is run an experiment with 20 different concentrations of substrate and determine the rates. Then I can go through and plot 1 over my rate versus 1 over my concentration. And what I should get out of that would be a straight line. What is the slope of that line? Km over V max. So on the slope alone, can I solve for Km or V max? On the slope alone. Okay, so the slope is 5. What is Km? What's V max?
You don't know it.
Okay, so the slope alone does not tell you Km or V max. Okay, so the whole point was to figure out what these values were. So based on the slope, we're still sitting in the dark. But do we have more information? What was B? One over V max. What is B in a linear equation?
Y equals
It's the y-intercept. Can we determine the y-intercept from our graph? Yeah. So what we can do is use our graph and determine the y-intercept. Where my graph went? Right here, which is b, which we know equals 1 over v max. Now with the y-intercept and my slope, can I solve for Km? Yeah. Do I need to know what K2 is? Or K1 or K minus 1? Nope. I've got a relationship that gives me all of that information now stashed away in one neat little constant that can be solved graphically. massively important. So our whole point is to get to this graphical interpretation, because now we've got something that we can say, oh, it has this type of kinetics associated with it. Okay? It's going to have this maximum velocity. Okay? Because maybe we don't know exactly how much substrate or enzymes involved in this. So what we'd end up having to do is do a whole bunch of different concentration changes versus our rates. Okay? And if we went through and did that, we may never reach the point where we hit the maximum velocity. So we would never see that plateau. But we don't need to see the plateau. All we need to see is the relationship between rate and concentration. And we can plot our Michaelis-Menten type expression into a Lineweaver-Burke plot, which is what this is called. And now we know what Vmax is. We know what the maximum velocity is for our enzyme reaction. And we can determine what that Km is. So those two terms are massively important to our understanding of what an enzyme can do. And it's all about trying to set it up into a format where we can see that as quickly and easily as possible. Okay? So, questions? It's okay. Take your time.
What is the 1 over V? What does the V stand for itself?
So V, and this is again one of those things that I found was kind of annoying about this. It took me a while to go back and check. Where did it go? It's all the way back here. I have no idea why I missed those slides around. Okay. V is equal to the rate for your reaction. Okay. So it's your velocity. Vmax is going to be your maximum rate because what happens? Eventually it levels off. You can't change it anymore. Okay, because you've oversaturated the enzyme. The enzyme can't turn over anymore. So this Vmax tells us something about how fast the enzyme can process, okay, which will push that further. Why did they decide to call it Vmax and not rate max? Probably because rate max involves more letters. Okay, it is quite literally probably as simple as that. Okay, so we end up incorporating a bunch of new symbols behind it. Okay, by that same logic, we can say, why did we write S and not substrate? Okay. S was easier to write out than substrate. Okay. So yeah, it's a bit odd that we bring in this V term, but really all we're trying to say with that V term is it's the rate. Okay. So we'll kind of whip through this again real quickly again. So our initial assumptions, we stepwise all the way back, is that we look at our overall equation, okay, of everything that's happening with that enzyme. Enzyme plus substrate goes to our enzyme-substrate complex to form our product. Okay, and when we think about and look at that expression, what we're trying to come up with is some way that we can understand how fast the reaction can go. Okay, and what those kind of rate constants are that are going to determine how fast the reaction can go. Because when we look at a rate expression, our rate expression is always rate being equal to some constant times our concentrations. Okay? Well, I would need to solve for the rate constant. If I can't isolate K1, K minus 1, or K2, I have no way of running a simple reaction just to solve for them independent. Okay? The only way I can solve for those rate constants is by looking at the entire reaction. I can't look at the individual pieces. Okay? So what we're trying to do is something complex is happening. Can you see through that? No, you can't. Something complex is happening inside this box. Okay? If you can't see it, what you're going to do is try and look at the inputs and the outputs. Those are the only two things you have control over. Okay? And so we can start changing the inputs to see what happens with the outputs. So we can decrease our inputs or increase them and see what happens with our output. Okay? And if it's a linear relationship, if I put 2 in, then I expect 2 out. Okay, within X amount of time. But with our enzyme kinetics, is it a straightforward, I may have to go back too far. Oh, and I broke it. With our enzyme kinetics, it's not a straightforward, and I can't even draw on it. It's not a straightforward linear relationship. Son of a... Okay, now it's listening to me. It's not that straightforward linear relationship that we see just with the substrate in our product. That gives us this weird hyperbolic curve. Okay? All of those rate constants are involved in this. And so we have to kind of come up with some way to represent and see those things, or rearrange our relationships so that we can see them more clearly and interpret them more clearly. Okay? So one of our first assumptions was to look at just the overall reactions and try and decide what happens at low or high substrate concentrations. Because at those low and high substrate concentrations, we do see linear relationships. That linear relationship can help us out. Okay? And that's where we got to these expressions. At low substrate concentrations, it's dependent on our enzyme-substrate complex. At high concentrations, it's dependent only on the total enzyme. Okay? And that's really important because it actually levels off. It plateaus. So that's a relatively easy one to solve for, except that I don't know what K2 is, and I have no way of solving for it because I don't know the concentration of my enzyme-substrate complex. Okay? At low concentrations, I have this new expression with my enzyme-substrate complex. Again, I don't know that concentration, so I can't solve for the rate. And I can't solve for K2. So what we have to do is make some simplifications. And what we go through and simplify is that we say that our reaction achieves a steady state. It achieves equilibrium. And our definition for equilibrium, anybody remember? The rate of the forward equals the rate of the reverse. Okay? So we're saying the rate of the formation of our enzyme complex must be the same as the rate of our decomposition. So we use that to give us a new expression. Once we have this expression, we say, okay, what can we do with it? Okay? With nothing else, we do everything to it. Okay? We can rearrange it, solve for the enzyme substrate concentration. Okay? But that doesn't get us anywhere. Okay? Or we go through and solve for it in group similar terms and hope that that works. Because if you think back to what you did in 152 or what you do in any math or physics class, ultimately what you do is group like terms. Because what happens when you group like terms? If you're really lucky, terms cancel out. Okay? And it simplifies your expression. Okay? So that's what we attempted to do here. And in that grouping, we end up with this expression. That expression on its own is pretty meaningless. Okay? But we think back to other things that we've already done. The other things that we've already done is we brought in this idea of a total enzyme concentration. And well, what is the total enzyme concentration equal to? It's going to be equal to whatever the concentration of the free enzyme is, plus whatever concentration of the enzyme substrate there is. Okay? We can use that to then solve for the enzyme concentration. Okay? Yes, that term necessarily brings in the enzyme substrate. And yes, we don't know that value. So why did we decide to solve for the enzyme and not the enzyme substrate? Because we probably didn't decide that. We probably tried them both. And what happened if we solved for the enzyme substrate concentration? We tried to plug things in, we didn't get anywhere that was useful. Okay, we ended up with an expression that we couldn't solve for. Okay, so when they did this, they tested thousands of different things. Well, that's probably only a couple things. Okay. Once we have that expression, we can now attempt to simplify, and we can slide that in. One of their simplifications when they did that is they said all of our constants come out as a new constant. So let's just define a new constant so I can simplify again my understanding or what I'm looking at. Granted, it does not necessarily simplify your understanding, okay, but it simplifies what you're looking at. We end up with this new expression with that Km involved in it. Okay. We can then rearrange that to solve for the enzyme substrate concentration. Why did we do that? Well, have we seen Km show up anywhere up to this point, except right here? No. So an expression solving for an unknown variable Km with nowhere to plug it in, not particularly helpful. Do we know the enzyme total concentration? Yeah. Do we know our substrate concentration? Yeah. So the only other thing in this expression that we don't know is the enzyme substrate. So let's solve for it. Again, we get a meaningless equation that we can't do anything with. But then that's where we have to think back to what other stuff have we incorporated. That other stuff that we've incorporated was looking at our rates. And our rates for low concentrations and high concentrations. Okay? And we can start to substitute in enzyme substrate into this. Taking a step further, we can compare those and say K2 shows up in both of these, which means I can now solve for K2. And I can set them equal in both expressions. Okay. All of these, what I would argue, are pretty massive leaps of saying, okay, now how do I plug this in or how I plug this in, is a lot of what happens in biochemistry and what happens in physical chemistry and quantum chemistry. And if you push into higher mathematics, calculus, right? Think of the higher ends of calculus. How'd you go through and solve the integral of the natural log of x over y? Okay? You had to go through and say, okay, how do I simplify that expression into something else? And you looked up somebody else's proof of what that integral was equal to so that you could then simplify. We're doing the same thing here. Okay? Except for you guys, you don't have to derive it, you just have to work with it. Okay? So we end up with our Michaelis-Menten expression. Big, holy crap, is that really true? 915? Oh my God. Gets us to our rates. If we now look at the meaning behind our symbols, okay, so if we go through all of this trouble, we now have a single expression that allows us to solve for both of these conditions. At low substrate concentrations, what happens? Okay, our rate needs to become equal to K2 times ES. So what we can go through and do is plug in some examples and see what happens to our overall expression. How does this affect our reaction? And we end up noticing some kind of patterns that fall out of it. Our Km ends up being a measure of how tightly our enzyme holds the substrate. Okay, well, does that make sense? Well, let's take a look at it. K2 was what? What's that?
It's a rate constant.
Rate constant for what?
Enzyme.
Decomposition of our enzyme substrate complex. What was K minus 1? Decomposition of our enzyme substrate complex. K1 was the formation of it. So as a measure of how tightly the enzyme holds the substrate, what would we expect? If it holds on really, really tightly, should we have a big Km or a small Km? Okay, so what we're saying is which sequence is bigger, the top or the bottom? If it's really holding on, the bottom needs to be bigger. Okay? So we end up with a small Km because our denominator gets really big. And so a division by a big number sets us up that way. So that can tell us how tightly the enzyme holds the substrate. Okay, is it going to be important for the enzyme to hold the substrate tightly? Yeah, but should it hold it too tightly? No, because then you can't decompose back to your products or get to your products. So that Km gives us some kind of understanding of how well the enzyme or the affinity of the enzyme for an individual molecule. How could we tweak this when we're trying to do drug design or targeting an enzyme's activity? We could design a drug that binds the enzyme super, super tightly. What would we expect to happen to the Km? We want a ridiculously small Km, because what's that going to do is now destroy the concentration of the enzyme, and it falls through the floor. Now, if there's no enzyme to do that reaction, whatever happens supposed to happen afterwards can't. Right? So what we can do is design things to give us better Kms, okay, depending on what we're aiming for. What happens to our Vmax? Well, the Vmax is something about the capacity or the efficiency almost of our enzyme. How quickly does it turn over to form product? Okay, and so that's our turnover number, or is related to our turnover number. See, did I put it there? Yeah. Our turnover number is defined as Vmax over the total enzyme concentration. Why do we have to bring in the enzyme concentration? What happens if we put in a lot of enzyme? What's going to be to our Vmax versus no enzyme? Vmax will change with our enzyme concentration. So our turnover number has to take into consideration our enzyme concentration as well as the maximum rate. Okay? It's our way of kind of standardizing that number.
What does it say for end? K?
It's referred to as kcat. There's another symbol. Another stupid symbol.
K-cat's good.
Your book references something else, I think.
K,
I want to say K-E, me?
K-E-Q.
I'm pretty sure it calls it something other than K-cat. I could be wrong on that. I thought I had changed it, but maybe I haven't. So just be aware that may show up in there. You will have to calculate your turnover number in the homework, but the turnover number is merely maximum velocity divided by the enzyme concentration.
Yeah, it says
Oh, it does just say K-cat? Oh, okay. Well, that's not too bad then. That actually kind of makes sense. Okay. So, graphical interpretation. Okay, this is kind of where we're stepping through. This equation allows us to see a relationship between our substrate concentration and our reaction velocity. And you'll notice that this expression does not look like a straight line. And that's because if we plot enzyme or our rate versus our substrate concentration, it's not a straight line. There were two sections that were linear. Okay, so if we change our substrate concentrations, we'll see that it linearizes out. Okay, that was kind of a weird way to say it, but let's try that again. What happens at high substrate concentrations? Stupidly, ridiculously high. What happens to this expression? Linearizes out to what? Not just flat. So that's what the curve says, but what does your data say?
It would be a 1-to-1 constant.
What would our rate be at ridiculously, stupidly high substrate concentrations?
0, essentially. Aren't you slowing down? You're like slowing down.
The rate of change of the rate changes, okay, but not the rate. The rate does not drop down. The rate is still going to be high.
It just flattens out.
It'll be equal to Vmax. If substrate concentration is stupidly high, what's Km plus a stupidly high number? Stupidly high number. Vmax times a stupidly high number divided by a stupidly high number. What happens? Stupidly high cancels, and we end up with Vmax. Our rate will equal our Vmax. So at ridiculously high concentrations, hey, this equation works. What happens at ridiculously low concentrations? Okay. Well, Km plus a ridiculously low number is just going to be Km. But what's Vmax times a ridiculously low concentration? Really, really, really low. What is our rate at low concentrations? Really, really low. This expression matches both of those conditions for our linear parts of our curve. Okay? So it's nice. It does correlate to it, but it's not the easiest thing to interpret. And that's where we switched to a linear relationship. Okay? That doesn't make this necessarily any easier to interpret, okay? But when we look at the curve, we can pull numbers off of it a little bit easier. Okay? Because I can figure out Vmax by looking at my y-intercept. I now know my y-intercept is 1 over Vmax. Boom, solved for. The slope of the line, okay, is now the relationship of Km over Vmax. But if I know Vmax, I can solve for Km. So that linear relationship allows me to solve for it very, very quickly. Whereas if we look back at this graphical interpretation, and I think I'm going to regret going backwards because I think I have it somewhere else, where is Vmax on this curve? Somewhere up here. Where? It depends where this line flattens out. Maybe it keeps going. So if you said your Vmax was actually here, is that your Vmax? No. Okay.
Is it your x-intercept?
So from this curve, you can't see Vmax. Okay. We can take an approximation. It is roughly in that range. Okay. And Sapling will ask you to do this. And I tested a few different numbers and locations, and it seems to be doing just fine. As long as you establish that Vmax is above that line, you should be okay. Okay?
It gives you a
So there's a decent range of error within that. Okay? I tried getting really, really close to the line, and I went kind of far away from it. And as long as you do the secondary interpretations off of it correctly based off of that, you should be fine. Okay. Let's see, because now, so there's our example plot. We can now draw all sorts of interpretations off of this. You'll notice that our line will continue out. We could potentially actually get Km off of the x-intercept, okay, which is a nice little fun thing that we could do. That's a little bit wishy-washy because do we have any data for negative substrate concentrations? No. Okay, so we are extrapolating the data backwards. Theoretically, it should be fine, and it should work out overall okay. So what we end up with is now at least two different ways to come up with and interpret some of this information. Step back from the inhibitor for the moment. I was hoping I had another slide there, and I did not. From this curve, we took a stab at saying what Vmax was. So let's say Vmax is here. Can you tell me what Km is? Can you determine Km from this curve? That's where this becomes a little bit weird. What happens at exactly 1/2 Vmax? So 1/2, we're going to look at this distance, and half of that is roughly here. What happens at that condition? Something is equal to something, I agree. So let's go through and solve. We're saying our rate is equal to 1/2 Vmax. Vmax times our substrate over Km plus substrate. Pull some fancy algebra around. Guess what you're going to find out? That's equal to Km. Okay. At 1/2 Vmax, your substrate concentration will be equal to Km. So you can pull Km off of this curve as well. Okay. Kind of a neat little feature. Okay. We are now, if that was not headache-inducing enough, this is where I think it gets even more fun. What happens if you have an inhibitor? Okay, so this is the tail end of Chapter 6, and it kind of carries a little into Chapter 7 as well. Okay? So in a normal enzyme, your substrate binds the enzyme, everything's good. But we have now a variety of possible inhibitors. So one type of inhibitor is a competitive inhibitor. In this case, what's happening is our inhibitor molecule binds to the exact same site where our substrate would bind. Okay? Locks it up and prevents the substrate from binding. Okay? So you then prevent product from forming. Okay? So it's a direct competition between your substrate and the enzyme. Okay? Are there other conditions? Yeah. There could be an inhibition, and this would be kind of an allosteric inhibition, where your inhibitor binds someplace else in the enzyme and causes a conformational change in the active site. If that conformational change occurs, that now prevents the substrate from binding, and that's what this picture is trying to show. Okay? Unfortunately, there's a variety of different non-competitive inhibitors. You have non-competitive and you have uncompetitive. Well, what does non mean? Not. What does un mean? Not. Why are we calling these two different things? Because they have two different mechanisms by which they work.
Because one affects the Km and one does not.
Yes. So what we're looking at is our standard enzyme. We can come up with a Km and a Vmax. Okay? So that's where we can pull in all this extra terminology. And I don't know why I wrote Vmax there like that. Okay? And so what we'd want to do is think through how would each of these things affect our Km or our Vmax. So if we look at a competitive inhibitor, what is it preventing?
Enzyme substrate complex.
It's preventing the enzyme substrate complex. Okay? So if we look at our K1, let's see if I can make sure I piece this together right. if we look at our Km and our competitive inhibitor, the enzyme substrate concentration goes to 0. Okay? It gets very, 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 very small. So what's a number divided by a really small number?
A really big one.
A really big number.
So your K.
Yes! Your Km increases. Sorry, I had to cheat. I had to verify I was right. Okay? So if you can't form the enzyme substrate concentration, your Km is going to skyrocket. So under competitive inhibition, the Km gets much, much larger. What happens with Vmax?
It's small.
So Vmax is when your substrate concentration is ridiculously high. So what happens when your substrate concentration gets so ridiculously high that it outlocates the inhibitor? What happens to the effective ability of the inhibitor to inhibit the reaction? It goes down. So what happens to Vmax? It should stay exactly the same, because the inhibitor is now, its concentration relative to the substrate is nil. So what you're looking at under competitive inhibition is that there is no inhibitor located at high substrate concentrations, which means Vmax for competitive inhibition should never change. The Km will absolutely change. So it will change how you look at your curve. Okay? But Vmax won't change. Okay? Non-competitive and uncompetitive. I actually forgot to put the definitions here, so let's take a look at these. Non-competitive binds to a site other than the active site at any time during the reaction. Okay? So what we're saying is that our inhibitor can bind either here or here. In both cases, it prevents the formation of product. Okay? It just shuts that down. In the case of uncompetitive, the inhibitor binds only to the enzyme substrate complex, but not to the free enzyme. Well, should that affect the rate of, or affect our controls coming out of this? Yeah, because in our non-competitive, we're affecting that initial reaction. We're affecting K1. Okay? In the uncompetitive, we don't affect K1. Okay? Because the uncompetitive only binds here, and K1 only involves the free enzyme. Okay, so we get a slight variance in how it affects the rates of your reactions. Okay? So let's kind of derive how this happens. So kinetic effect for non-competitive. And we're already given an answer here that Vmax decreases. Okay, what we're saying is we prevent product formation. Would we expect Vmax to decrease? We're saying that I cannot do K2. Should Vmax decrease?
Yes.
If K2 disappears, Vmax is going to have to drop. Okay, we would expect Vmax to drop under those conditions because we're preventing the formation of product, period. Okay. What happens to the Km? Well, if we look at the Km, our Km is K2, okay, which is prevented. K minus 1. What happens to K minus 1? No change. What happens to K1? Okay. Careful. What happens to K1? When does our non-competitive inhibitor bind? At any time. It will affect K1. K1 will decrease and K2 decreases. If both those terms decrease, they cancel out. What happens to Km? Remains unchanged. Okay? If we look at the uncompetitive inhibitor, okay, it only binds the enzyme substrate but not to our free enzyme. What ends up happening now is this will affect both Vmax and Km. You'll notice that both of them decrease. Those relationships can be kind of derived out of looking at what Km means and what Vmax means, which is what I was doing for the non-competitive and the competitive. Okay? But I'm going to take a stab at it that you guys don't like trying to figure that out. Okay? I find it exceedingly hard to see. And as far as I know, only one person I've ever met can see and pick up those relationships quickly. Okay? What you are ultimately responsible for is for competitive inhibition, what happens? Vmax is unchanged, Km increases. You're responsible for that. Okay? For non-competitive, Vmax decreases, Km remains unchanged. For uncompetitive, both Vmax and Km decrease. That's why those things are in bold. So if you memorize those, you're pretty much set. Okay? Not quite just as simple as that, because how do we determine Km and Vmax? By looking at graphs. So what we need to be able to do is say, this is a standard enzyme reaction. What happens if we have these inhibitors involved in it? How does that affect the graph? Okay. So for competitive inhibition, I'd gotten all theoretically excited about trying to go through and solve this, and I have since really given up on that because I just can't seem to pull all the algebra together to do it. And have not found a literature source that actually cites all the algebra behind it. Okay, but theoretically, it is possible to go through and do it, and what you'll notice is that the slope changes. Okay, why should the slope change? Because the inhibitor is affecting Km. It does not affect Vmax, which is why B, our y-intercept, will be the same. So if we go through and look at a graph, our no inhibitor line, okay, with that blue, as soon as we add a competitive inhibitor, what happens? Well, Vmax does not change, and Vmax was our y-intercept. Okay. So everything stays constant through there, but our Km increases. Well, if Km gets bigger, what happens to 1 over Km? It gets smaller, so your slope starts becoming steeper. Okay. So it's recognizing what those changes do in your overall graph. Okay. What happens with the other graph? So we now add a competitive inhibitor. We'll call it purple. Does purple show up okay there? Maybe orange. Orange shows up a little cleaner. What would we expect to see with a competitive inhibitor on that graph? Our rate versus our concentration. What happened to Vmax? Should stay the same. So I would expect roughly the same line up top. Okay. What happened to Km? It increases. Where was Km in our reaction? It was at our half Vmax. So half Vmax, somewhere about here. For Km to increase, where does my orange line need to zip through? On this side, on x or square?
X.
Km needs to increase at half Vmax. It needs to be on the square side. Because now when I drop my line down, Km has gotten bigger than on the other side. Right? So if we have a competitive inhibition plot, if we compared it back to the standard, what we would see is a smaller slope to begin with, and it should level at the same point. Okay? So two different ways that we can see this graphical information pop up. Okay? We are out of time, but what I expect you to go through and do, pretty much ignore all of that. Look at your graphs for non-competitive inhibition. Same idea. What happens to the line when you have a non-competitive inhibitor? Okay? Which comes back to what happens down here. Km remains unchanged. Well, Km was our x-intercept information. Same point. Our kinetic effect, your Vmax will decrease. That affects, okay, the slope at the end, okay, where it crosses the y-axis. How does it plot out? Well, if Vmax decreases but Km stays the same, I don't have enough time to get the Km just right, but we would expect a line lower for your Vmax. Right? And your Km should cross the exact same point. So there's half there. Yeah, so I didn't draw that very well. Right? I think it's actually going to go through something like this. No, I drew that wrong too. But you should be able to figure out how to draw that. Same deal is going to happen with your uncompetitive inhibitors, and the program is just about to die. Same deal with those graphs. Okay? The last one that your textbook will throw at you is mixed inhibition. Okay, what's happening with mixed? Both your Km will increase and your Vmax will decrease. Okay, that's when you have all sorts of different things happening. Does it make sense for that to be true? Well, what happens in uncompetitive? They both decrease. In non-competitive, one decreases, one doesn't change. So if you have a mixed situation, you're going to get everything going pretty much haywire. Okay? So you'll see that pop up when you look at your sapling homework. Okay? I will go back over this on